Welcome everyone to the afternoon session. And it is my pleasure to introduce Alessandro Alla from Sapienza, Rome, and who will tell us about efficient data-driven regression for reduced order modeling of the spatial information. Alessandro.
So, thank you for the presentation. Tudo bem? Okay, first of all, let me thank the organizers to organize this event, to invite me. It's a pleasure to be back. So I took initiative here. I slightly changed the title of the conference in a mathematical way, because in Italy it's bad luck to say happy birthday before the day of the birthday. So this is tending to. So I took this initiative, and I'm a bit impressed how Carlos can have so many connections even without having a mobile phone in 2025. I can
Everybody has it.
Yeah, exactly, but you know. And of course, before going to math, I want to give you. I want to share a couple of things. You might know, or you might not know, I was professor at PUC-Rio, and when I sent my CV, I was in the US, looking for a professor position in the US, and the math jobs appeared at PUC University. That honestly, I didn't know anything about PUC. And I got shortlisted, as you can see from this email by Marcos, who was the head of the department. And that was the first time in my life that the name Carlos Tomei appeared in my life, here. So essentially the mail is saying that you are shortlisted, but whatever you have to ask, just contact Carlos, because Carlos speaks Italian, and I'm Italian. So then the second contact with Carlos, I'm not sure if you speak Italian, but basically the follow-up email was by Carlos, and it was like, just feel free to ask whatever you want. Somehow, right, Carlos? You want to better translate? No. No. But I guess he regrets that, because I took seriously this email, and I started to contact him for any single thing. Then. Yes, I think he regrets. Then, you know, in Italian we still have this formal way to talk with the person who are like older or wiser, whatever. And Carlos, in a second mail, told me like, just forget it. Just tell me you. In Brazil we don't really have this. This distinction. In Italy, you still have, so it was very nice. Then I came here to Rio for the job interview, which actually was my goal. I send you my CV. In the worst case in the best case scenario, I can spend 1 week in Rio, and that was what happened. But then I met Carlos for 1 week. Carlos was my guide. He was my driver. He came to pick me up and bring here. And I was always talking with him, going around PUC. It was a bit hard to talk to him when you are around PUC, because everybody knows him. Everybody. But he always has some history, something to tell you about the people that you meet. And then I accepted the position. And here I have a picture, a shy picture, that so Carlos came to pick me up at the airport the day that I arrived to move in Brazil, which was the 11th of September 2017. And I took a selfie, but I was like shy to ask Carlos to take a picture together. And you see that he's carefully driving, and I'm taking a picture, also to say, Mom, that I'm in a good shape. And by the way, so Carlos was wearing shorts, and yesterday I saw him and I was surprised that he was not wearing shorts. And today, second day in a row that I've never seen him 2 days in a row without shorts. And today even more, he has a shirt. So that's, that's unbelievable what happens. And then the day after, he came to pick me up at the hotel. Long story short, I didn't find a place where to stay in Rio because Carlos told me, we will find something, you know, a very Brazilian way. Then I arrived and he was like, I don't know where you can stay. So I went to some hotel in Ipanema. He came to pick me up, and the day after, you see that both we were already having a picture together. I asked him, like, shall we take a picture? Then last time that I met Carlos was in January that I came here, and there was I mean, sometimes when we meet, we go around Ipanema, we work together. And yes, so Carlos is almost 70, almost. Okay. Before I forget, I mean, I'm just copying what Andrea did. I have a little present for you as well. Yes, but I have no nice bag for you.
Oh. Thanks a lot.
Before I forget, so Carlos likes to take his Italian alive, so he plays crosswords in Italian. Okay, so time to go into math. So as someone mentioned already, so the topic of my talk is not connected to anything you have seen so far. Okay? Just feel free to stop me anytime that you have a question. But the main mathematical tool which is behind whatever I'm doing is the singular value decomposition, which I hope it's known. I also slightly changed the title of my talk. So this is more about data-driven modeling. So in a sense, what I want to do, I want to discover a differential equation. So I have a set of data, temporal data, okay? And I want to discover the equation, the differential equation which is behind in a very efficient way, okay? So this is the outline of my talk. In particular, what I will, so the data that I will study, they come from a model which provides Turing pattern. I will explain what is a Turing pattern. Then, first of all, I will do something about model order reduction. I will show you a couple of results on model order reduction. And then I start doing the data-driven modeling. First, about using the dynamic mode decomposition and some improvement for dynamic mode decomposition. When I say dynamic mode decomposition, is a way to fit a linear system, in linear differential equation. Okay, then the extension to the polynomial model, some experiments and conclusions. Okay, so the model that I have in mind is a coupled system of reaction diffusion equation. Okay, so U and V are the two variables. Okay, it's a two-dimensional problem, coupled two-dimensional problem, and F and G are two nonlinearities that they are connected, and usually those are polynomial nonlinearities. For example, if you see the DIB model, you see that you have U and V that they are connecting. Sometimes they do multiply each other, but they do have a polynomial structure. So for that model, what you can find a steady state solution. So that means that for a very long time simulations, at a certain point you get a steady state, okay? And according to the parameter configuration that you have, you get a different pattern, okay? You can see, for instance, you have spots, reverse spots, labyrinths. So according to the parameter configuration, you get this, you get different kind of patterns. So what I want to do numerical approximation, okay? So I have the continuous model. I discretize and I get a system of, a very large system of ordinary differential equations. Here I'm using simple finite difference, and for instance, the matrix A is the discretization of the Laplace operator. And so nevertheless, we have a very simple structure, U dot now, which is the time derivative, okay? So what we have, depending on the mesh size and how large is the domain, we can get a very large system of ordinary differential equations. So this, from a computational point of view, from a numerical point of view, can be very, very expensive, because you want to get, so you have a special dimension which is very high when you discretize, plus I want to get a steady state, and for this problem, steady state can be reached for a very long time horizon. So it can be very computational. And when I say this can be very high, I'm thinking of something about dimension 10,000, okay? 10,000 is already high for me. So in order to discretize in time, I'm using an IMAX scheme, which means that I use, for the linear part, I use an implicit scheme. When we have a nonlinear part, I use an explicit. So you see here the implicit part and the explicit part. There are also some improvements that where you can use a matrix-oriented approach, but this is not interesting for what I want to say here. So usually to get the Turing pattern, you start with a perturbation of equilibrium, and the equilibrium is computing by the nonlinear part. So usually you have some equilibrium, and you perturb this equilibrium in order to get the pattern. And also there are two indicators that are very interesting and useful. One is the mean of one of the two variables, and also the increment. So this is the discrete increment. So this measures how big is the difference between the k iteration and the k plus 1 iteration, okay? So this will go slowly to 0, and then, I mean, in a certain tolerance, then that is an indicator that you reach the pattern or the steady state. So the challenges for this problem, for numerical challenges, is, as I said, the large spatial domain. So if you have a very large spatial domain and you put many points, you have a very high dimensional discrete problem. And also the long time integration. So if you want to get to the steady state, you have to integrate the problem many times. And also, since the problem is very stiff, in other words, the problem can be very difficult to integrate at the beginning, especially because lots of happening from a physical point of view. You also have to integrate with a very small temporal step. So, okay, those are the challenges. So one idea here is, instead of doing the standard finite difference, is to reduce the dimension of the problem using some orthogonal projection. And the idea is that if the high-dimensional discrete problem is dimension n, you find a subspace of dimension r, which is eventually way smaller than the original dimension, and you reduce the computational cost, provided that you have a way to find the orthogonal projection. I mean, something which reflected the problem. So on one side, we can reduce the computational cost. On the other side, we want to keep the accuracy, okay? So it's not that, I mean, there is a trade-off, because you reduce the computational cost, but you get a solution which is completely far from the one that you get. It makes no sense, okay? This is the trade-off. So let me briefly mention here one technique to do the model reduction, which is called proper orthogonal decomposition. So the idea is that, as I mentioned, I want to project the system into a subspace which is low dimensional, okay, lower dimensional. And how can I do the projection? I assume to have some data on the system, okay? So those are snapshots of the first equation in U and snapshots of the equation of V, okay? So here I assume that I have access to the finite difference schemes. I store some of the data, and those are the snapshots metrics for U and V. So once I computed this, I compute a single value decomposition. Actually, I do a truncated single value decomposition, okay? So I do the truncated reduced single value decomposition, and actually, the basis that I'm going to use to project my problem are the left singular vectors of the matrices SU and SV. Those are the bases that I'm going to use. In fact, what I'm going to suppose that U and V can be decomposed by, sorry, just in the wrong place. Can be decomposed as a multiplication of the bases where I'm projecting. Those are orthonormal matrices, okay? And some coefficient that I'm going to compute. Now those coefficients will have dimension R, which is way smaller than the original dimension. And then we impose Galerkin projection orthogonality in order to reduce the problem. In fact, I mean, if you plug this assumption, then you multiply by CU transpose and CV transpose in the right places, you get something which is reduced dimension. Okay, then there are some other works that you can better compute the reduction, the F and the G, but still the idea is that you have data, you compute the singular value decomposition, and you project the system according to this singular value decomposition. Okay? So this is a straightforward approach, but in many cases it works, not in this case. In fact, this is the pattern that we wanted to achieve. So this is the singular, this is the high dimensional problem, and this is the approximation that we got using the POD. So you see that we completely failed in this case. Of course, here the rank of the truncation is quite high. In general, what we expect, the higher the amount of modes that you take, so the larger R, the better approximation. So here, this amount was close to the rank of the snapshot matrices, but still it was not really working. And you see the mean is completely wrong, and also here the error is not decaying according, or I mean, sometimes it's decaying, but it's not monotone. Usually what you expect, you expect to have a monotone decreasing error over the reduced space. So what we observe with us is a straightforward approximation with straightforward application of POD is that we got a big oscillation of the error, and also I did not really talk about the dime, but this is the hyper reduction of the nonlinear part was also not stable. So the goal here was to stabilize the error for the POD, basically. So what we did, long story short, we added a correction term in the model, which was based on the basically to correct and to add some more information that in the reduced model were missing. And you see here, for instance, so the C means a correction, and if we do pod with correction, we could get what we wanted. So a decay when the dimension of this the reduced space was increasing. Also, the time, you see here the computational time. This is for the high-dimensional model, and this is the computational time. For instance, if I do PODC, you see here that we are faster. So this is not the best option because we are dealing the nonlinearity. We are not dealing efficiently with the nonlinearity. But for instance, if we have a better approximation of the nonlinearity, you see that we get almost one or two orders faster than the high-dimensional problem. So this is just to mention that that was my first time working on the Turing pattern and on something on model reduction. All right. So now I want to do data-driven modeling. Okay. The first idea is to use the dynamic mode decomposition. Let me give you an idea of dynamic mode decomposition. So this is a purely equation-free modeling. I have data over time. So for me, x0, xm, that means something that I can get at time t0, t1, till tm. And I want to fit with an equation of this type. Linear, very simple. So basically, what is the unknown here is the matrix A. This is the unknown part in the model. How do we do that? We want to do a fitting. Okay? So we do linear regression. how do we do that? So we split the data into two matrices, and we assume to have a linear relation with the data, okay? So you see here that I assume that the solution, the data times tk plus 1, is linearly linked to the previous one at time xk. So essentially, we want to solve a least square problem, and the solution of this least square problem, so where the A is the unknown part, can be done using the pseudo inverse. Okay, you can do using the pseudo inverse, or I mean, what you can also do, you can also compute the eigenvalues and eigenvector of the matrix A, and those are the DMD modes. Okay, but in practice, you have data, you want to fit, you find the linear matrix, and that's it. That's what you need to build the system. On the other hand, if we have very high dimensional data, the pseudo inverse can be very expensive. So if the pseudo inverse can be very expensive, there was a second algorithm which was introduced in 2014, which is called the XADMD. Basically, the regression is not computed in the high dimensional space, but in a projective space. So we do again a projection. So how does it work? Again, we split the data, we compute a reduced singular value decomposition on rank R, and then we make a projection on the matrix A. So we do some computations, and at the end we have a projection on the matrix A, which is now R by R. So now everything is simpler. So what we are looking now is a low-dimensional system to fit our data. Okay? So in that case, we also can get some more efficient result. Then also here, in this case, we can compute eigenvalues, eigenvectors of the matrix of the reduced matrices as an approximation. But again, the very interesting fact that we can build the unknown matrix. So then we can get different strategies. Since here we have a coupled problem, we can get snapshots, two different snapshots matrices, one for U, one for V, or together. Okay, you see here that if we have U, V, then this is we double the dimension. So there is literature. We applied this strategy to the Turing pattern, and again, it was failing. So you see that this is the dimension of the truncation, and you see the error is really increasing. The condition number of the bases is diverging, is very high, but with both strategies, the dynamic mode decomposition was not working. So then, what we did a very simple idea, which is based on the bisection or a piecewise approximation. So instead of working with the large horizon 0 capital T, we started to split into smaller problem. Okay? So I remind you that what we are doing, we have a nonlinear problem, and we want to approximate. So we have a nonlinear dynamics, but we want to approximate it with a linear dynamical system. Okay? Sometimes it's possible. Sometimes if the problem is very nonlinear, that is not that easy. So then, we split our snapshot set into smaller system according to some error indicator. But now, for each of these, we have a smaller interval, and in each smaller interval, we apply dynamic mode decomposition. Okay, so we call it piecewise dynamic decomposition, and then we did the reconstruction over the whole horizon. We had some time horizon, not time horizon. We had some error indicator to understand how many subintervals we needed. Okay, those were based on the error approximation, some relative error for the data or for the matrices. But I will not go into these details. And but I would just want to convince you with a couple of examples. One is about the Fitzhugh-Nagumo, same structure of the reaction diffusion. So those are the two nonlinear terms, F and G. You see here that we have U to the 3. This is quite decoupled because you never multiply U and V, but still this provides a limit cycle. So it's a periodic solution, and it's not that straightforward to get with a linear model. In fact, you see here that if we apply directly DMD, this is the mean solution for U and V. You see that they do not match. Okay, it's completely wrong. Instead, if we use so those are the limit cycle. You see the mean of U and the mean of V, and I mean it's clear that they do not coincide. Okay, so dynamic mode decomposition in this case is not working, and actually this picture reflects the best error that we could get for some R, but still you see that it's not good. On the other hand, if we apply this piecewise dynamic decomposition, what we could get a better approximation over the number of subintervals. I mean, this is quite intuitive. If we increase the number of subintervals, we are getting smaller time horizon, or interval horizon, okay? And then we get better results. And also here you see that if we are using piecewise dynamic mode decomposition and compare with data, they do almost overlap, okay? So we made the problem easier because we were splitting into small intervals, but that was working, and we also got a monotone decay of the problem. Also, here I just want to tell you some other benefits. Here, for instance, the rank that we got in all the subintervals, even if we have a larger number of dynamic mode decomposition to perform, then we were getting smaller and smaller reducing of our decomposition. So that means that also the dimension of for each subproblem was smaller and smaller. A second problem is a lambda omega system, which was generated spiral waves. Here you have just F and G, the two nonlinearities. This is the dynamics of the problem. You see, you start from 0, and then you start to get this spiral wave. And again, if we apply dynamic mode decomposition, it's clearly that we are not getting anything accurate. On the other hand, here you see that we already have, with the 10 subinterval, we're getting a relative error of 10 to the minus 5. A little bit erratic, but still we were always in that range. And here you see that the mean of U and V, they are on the top of each other. So we could get a better approximation of the dynamic mode decomposition in this context. All right. Let me drink some water. So before getting to the extension to the dynamic mode decomposition. So again, I have the same problem in mind, but I want to extend the dynamic mode decomposition to polynomial systems. Okay. So to do that, I want to recall the dynamic mode decomposition. Okay, the dynamic mode decomposition is an extension of dynamic decomposition, clearly. So if A0 is 0, we have a dynamic mode decomposition. Okay. Now we want to extend with some external input. They call control, I think, as an input. Okay. So this is the structure that we want to fit now. So we have data and control. Okay, so now we have two kinds of input. And again, as a dynamic mode decomposition, I'm splitting the set of data into two parts. So here, I'm using the derivatives of the finite difference derivatives of the data on the left part, and on the right part, the data that I have. And here I have the control input that those are given. So then I can augment my, basically I augment my linear regression problem, okay? So you see here that the metrics that are unknown in the problem now are A0 and A1. I collect in a matrix bold S, and omega, C, and those are the given part, okay? So our assumption is that the left part, which are the derivative, can be approximated by this product S and omega, times omega. S is A0, A1, and this is the control and the right part of the data. Okay? Again, how do I solve this regression problem? Pseudo-inverse. And then I need to do a second single variable decomposition in order to further project the problem. And at the end, what I get a data-driven model, which is in a low-dimensional fashion. Because now, the index R is to indicate the dimension of the reduced problem. Okay? But nevertheless, I was able to get A0 and A1 in order to fit the problem. So motivated by the dynamic mode decomposition, we want to extend this approach to, let's say, a polynomial structure. So now the structure that I want to fit is similar to the dynamic mode decomposition. So now we are adding a constant part, which I call A0. And then I have a linear combination here, same matrices times. So this is the polynomial structure. So basically, if D is equal 1, this is again the dynamic mode decomposition plus a constant part. Okay? If we have 2 here, we have the dynamic mode decomposition plus a quadratic term. Okay? So this is a product, a Kronecker product that I have suggested, I've recorded here. So this is a Kronecker product of the data that I have. Okay? So according to the D, I have this polynomial structure. So if D is equal to, I have a quadratic differential problem. Still in the high dimensional setting. So what I need to do, I need to do a regression here again. So this is the problem that I need to do in order to get A0 and the matrices AI. But again, this is very computational, very expensive. So we need to do projection. So the key idea is that we have data, we have to do the projection of the data, and then we do the fitting. How do we do the fitting? We do the singular value decomposition, truncated singular value decomposition. We project the data, and then we solve this minimization problem. Now this is feasible because the dimension is very, very low. And if we do the low dimensional, we can do the pseudo inverse now, and we get all these matrices. So in detail here, I have to augment my matrix here. You see that I put all the unknown, supposing that D is the dimension of the polynomial structure. I get A0, R, A1, R, and so on. So this is already in the low dimensional space. I cannot do in the high dimensional space. So those are the omega R. So those are the data. Remember that I have data, and I need to compute all the Kronecker product here. This might be computationally expensive, but I can also use the symmetry of the product in order to make it more efficient. And that at the end, I have to solve this least square problem, and which is given by the pseudo inverse of the matrix omega R. Okay, so clearly this is also expensive as D increases. In the numerical example that I will show, we did the D equal 2 and D equal 3, and of course D equal 1 because that is related to the dynamic mode decomposition. So the choice of D is also constrained by the rank of this matrix in order to have an overdetermined system. So we have some limitation. And also, since this problem can be very irregular, I mean, this is a least square problem, we do some regularization in the computation of the pseudo inverse by neglecting very, very small singular values. Okay, this adds some regularity for the least square problem. So, and at the end, the reduced model that we are going to learn is of this form. Okay, similar to the one that I showed at the beginning, but in a low dimensional setting. So this one is somehow a generalization of dynamic mode decomposition. We do not have a control, but instead of a control, we are having this polynomial structure. One can also think that the control is given by something which depends on the state in a sense. And as I mentioned, if D is equal to 1, so this is just a generalization of dynamic mode decomposition, which was proposed by Liu and Tartakovsky in 2021. So to summarize here, this is the algorithm that we are proposing. So we have the data and we split the data. So one reflects the derivative of the problem, so numerical derivatives, and the data of the problem. So we compute the singular value decomposition of this matrix, truncated singular value decomposition. We project our data, and then we compute the we do the projection, and then we compute all the matrices AI R, so the reduced matrices. And then, since we get a low-dimensional system, this is also almost inexpensive to integrate the ROM. And at the end, since we have some basis, we go back to the high-dimensional problem. So let me try to convince you on a couple of experiments. So what we did here, we did a comparison for D equal 1, 2, and 3. And so having in mind that we want to do approximation for Turing pattern, so at the beginning, what happens in the Turing, when we have this kind of simulation, those are very nonlinear at the beginning, and that's very hard to approximate. So we decided to collect data in order to avoid this, to not get information about the first steps, the first temporal steps of the problem, and we choose the data set according to this structure. So this one is the first data we collect that has nothing to do with the initial condition of the problem. And we fix M in order that we satisfy this ratio. So that means that we want to measure how close they are the first initial condition of the model and the final one that we use to train. And also, this one does not coincide with the final time capital T. Because what we wanted to test is, since we have we want to get to a steady state, we also want to get an idea or how good is this model in understanding what is happening. So in order to get some extrapolations or some future state predictions. So in fact, what we are doing, we train the model in a certain temporal domain, and then we test it in a second temporal domain till the end in order to see if we were able to get the pattern. In fact, we did the projection, and the set of solutions can be interpreted by the solution, the approximate solution in the training regime, and the extrapolation, so outside of the training regime. And we were using two error indicators. One is for the training, so this is just a relative error in the Frobenius norm inside the training, and this is the error for the final pattern. Okay, just the time, just the relative error at the final time. Of course, I mean, somehow we get the data. We do not need to know anything about the model. But we know the model that is behind, so in order to check the quality of our system. So we have two different tests here. One is for the Schnakenberg model. Here you see F and G. This is the parameter configuration. So here the final difference, we ended up with something of dimension 5,000 if we are coupling. And this is the domain where we are training our data-driven model. This is the domain, the temporal domain, and our capital T, the final time should be 2. So you see that we have a little window to train and a very large window to test our problem. So this is the final pattern that we want to get, just to give you an idea. So those are spots. And those are the differences that we have between the first solution used to train the problem and the last solution to train the problem. And you see the difference. This is in log scale, and this is the difference with respect to the final pattern. So those are the error indicators in the training regime for d equal 1, 2, and 3. So you see here, and those are the number of modes, the R that we're using. You see here that we have a monotone decay. Also, if you remember at the beginning when we were using model order reduction, so not a data-driven model, we were not able to get a monotone decay with respect to the dimension of the reduced space. So here, looks like that we also get a model that is performing better when we increase the dimension of the reduced state. And you see that d equal 2 and d equal 3, they almost coincide in this case, but still they are better than d equal 1. At a certain point we got stuck and we did not improve our approximation. Here, this is the extrapolation error. So what happens outside of the training window? If we do d equal 1, you see that the error is increasing, is blowing up, okay? If we do d equal 2 and d equal 3, here you see that we get something of error -3 up to some regularization probably. You see that we have a decay, okay? So we perform better than the case d equal 1, and this is what we expect, okay? In terms of speed up, I mean, the reduced model was way faster than the high-dimensional model. Those are the speed up factor compared to the relative error. So how to read here? So if we want to have with d equal 3, we got almost 100 times faster than the d equal 1. Okay? So if we want to get something to this error, you see here, and you probably have something like 50 times faster than the high-dimensional model. And so on. Second pattern, this is another model, which is called, I guess, Mimura-Tsujikawa. Actually, with respect to the model that I proposed at the beginning, there is an extra term, which is a divergence, a nonlinear divergence, but I'm not going to get into detail, but nevertheless, we still get a pattern here. So the final time is 500 here, so that's very large. This is the time window where we train the problem, and then we test the extrapolation from 210 till 500. So it's very large window. This is the history, how we got to the pattern for this model. You see that it's very slow. For instance, from time 33 to time 100, it's hard to see a difference, for instance, right? Then something is happening, and then slowly we are getting towards the pattern. And this is the final pattern that you get from this model. Again, the error behavior, here you see that we get something a little bit better when we have d equal 2 and d equal 3. But what was very interesting for us was the extrapolation error, okay? That also in this case we could get better accuracy in the extrapolation error. And of course, the quality, the accuracy really depends on how much you train the model, okay? So for instance, if you get a better training, so you get a training closer to the pattern, you can also improve the accuracy of the extrapolation error. So remember in the previous picture we got something which was -3 as an order of accuracy. Now you got the negative. But this is also intuitive. The more you train, the better you can get. So let me bring to conclusion. So I tried to basically explain 3 different things applied to Turing pattern, or in general to reaction diffusion system. To do model order reduction, to get some stability of the model reduction, we did a correction term. To get a dynamic mode decomposition, I introduced the piecewise dynamic decomposition, and then at the end, an extension of the dynamic mode decomposition towards having a polynomial surrogate model, basically. So in future, what would be interesting for me is to do many query scenarios so that with one model I can deal with many different configurations. This is quite challenging because of the nature of the system. Also, on the other hand, doing a parameter identification. So I give you I give you the data. I want to find what is the model behind the data. That also might be used to train machine learning machinery, basically. So those are the references for the talk. The last part is a work in progress, and which should go soon on archive. And with that, I would like to thank you for your attention.
Questions? Alessandro, can you comment about the robustness of this variation of DMD for noise? Because you presented a case where you used it to construct a reduced order model, and your observations came from a medical simulation, more or less controlled. But imagine you have
so in general, I mean,
from experience or numerical simulations in a coarse mesh or with unstable algorithms that your observations are very polluted with noise.
Yeah, I mean, first it depends on how much noise. I mean, it really depends on how much noise you have, right, on the data. And in general, when you have a data-driven, whatever that depends on data, it's hard to predict in advance. I mean, it really depends on data. It's case by case, right? So one thing that I can say, usually when you have a noise and you do a singular value decomposition, this is a way, a first way to do some denoising, okay? But in general, it's hard to reply to this question because it really depends on the quality of the data. So here, yes, we assume that we have somehow nice data. Yes, I do not claim that I have noisy data. But in general, it's really case by case, in my opinion.
If you allow me to give a brief suggestion.
Sure.
When you have the truncated decomposition, you may experiment, throw away some modes, and see if this helps to the noise in a few ways. Because the signal.
What do you mean? What do you mean by throw away some nodes?
You have the matrix. You made the truncated SVD. The signal is more or less concentrated in the first modes, and the noise is typically more or less distributed among all the modes. If you truncate the truncated one, throw away the last modes, maybe you can.
So you are suggesting to do a single value decomposition of the single value decomposition.
You
okay.
compute the reduced order basis and experiment. So if I throw out the last 10, the last 20, is this better? Maybe you can do this inside your algorithm.
Okay.
Create some metric to quantify the quality.
Thank you.
Just an idea.
So the first part of your talk about the POD that you showed that it doesn't work, and then you said that, oh, there is this correction that you didn't talk about.
No.
Can you talk a little bit about this?
So the correction basically we added some missing information on the system. So I'm not sure if you're familiar with the filtering methods for Navier-Stokes or something like that. But essentially, so we saw that the surrogate model was not that good, okay? So that means that some information were missing. So we added something based on the high-dimensional system. So we were adding something more in order to provide the missing information. That is, but I mean, we can talk more if you want, for sure.
Because sometimes when you do system like the first one that looks like Hilliard, this kind of phase field. So if you do SVD, your vectors are not going to be between 0 and 1. Navier-Stokes, like you do the SVD and then you get negative energy.
Yes.
Points. Right?
Yes.
You have to do correction.
Exactly.
Okay. So I don't know in your case if it's related to that or.
I mean, what you are talking, I think it's something some people call structure preserving model reduction. This is not structure preserving. No, it's not that. So the correction is based on work by Trajan Iliescu. I'm not sure if you are familiar. And they were for filtering of fluid things. Okay, so we applied in this context, and then we did something. But I can give you more details.
Okay, so thank you very much.